Now let's try the problem number 36 from chapter 6 review exercise. We'll complete these three parts for this problem. For convenience purpose, I copy paste this problem to my notebook. Let's take a look at this problem. We are given a region R, and this region R is bounded by three curves. The first one is this quadratic equation. The other one is a linear straight line and the x-axis. So the first question is we need to set up a single integral that gives the area of R. Now let's zoom into this graph, and we should give a try. Try slice the region vertically and horizontally, then you can see which way to go so that a single integral is needed for the area. It's just one single integral. Let's slice it vertically first. From here, you can see that when I slice the region vertically, in different places of the region, the vertical slice hits different functions. So this is telling us that vertical slice will not give us a single integral, right? We have to do more than one integral to find the area. So we cannot do vertical slice. We have to do horizontal slice. So let's do horizontal slice. And we can see that this horizontal slice, the right hand side of the slice is the straight line, and the left hand side of the slice is the quadratic equation. So this is true in the whole region. That means that's the way to go, right? So with that, let's try to set up the integral. Before we set up the integral, we need this intersection. Let's solve this intersection, the coordinates of the intersection. Now from these two equations, we can see that probably a substitution is easier to solve for the intersection. So we can quickly plug this x in the second equation right here. Okay, let's do that. So by doing the substitution, y equals x minus 4, right? So x is y squared plus 2. And drop the parentheses and move the r to the right side. So we have y squared minus y, which is from the left side. Plus 2 minus 4 gives us minus 2. Now left side is just 0. And we can factor this quadratic equation and then solve for y. And we can see that y is equal to 2 or y is equal to negative 1. From the graph, you can see that 2 is actually the solution. The negative 1 is down on the bottom, maybe somewhere here. So that's where the next solution is. So we don't need this solution. Y equals 2 is what we want. When y equals 2, if you plug in this equation with y value 2, you see the x value is just 6. So we do know this is 6. This point is 6, 2. Okay. We have done enough preliminary work, so we can now continue on part A. As we discussed before, we have to slice this region horizontally so that we have just one single integral for the area, right? And this slice can be made from 0 to 2 in this region. Therefore, the limit is 0 to 2. The way we slice it horizontally, that means we are integrating with respect to y. The integrand will be the length of the slice, and we always use the large value of the slice minus the small value of the slice, the right minus left. And because it's dy, you expect only y variable occurring in the integrand. So you are gonna solve for x and plugging x into here, right? So which means y plus 4 from the first equation minus the second equation, which is the left side. It's from the x equals y squared plus 2, so we plug that value here, and this is the integrand. Okay, so this is the single integral we need for part A. Now for part B, as discussed before, this region is rotated about x-axis, and we have to cut this region, slice this region horizontally. Otherwise, if you slice it vertically, you have to have more than one integral for the volume. So let's look at what will we get if this slice is revolved about x-axis. I'm gonna try to draw. So this slice, when this slice is rotated about x-axis, we can see that a cylindrical shell will be generated, right? Okay, so this is the cylindrical shell. Because of that, shell method should be used. Now, let's try the shell method. The way we slice it is going to be dy, horizontally slice, because, and again, the same reason, this slice goes from 0 to 2. And here, the cylindrical shell method tells us it's going to be the circumference of the shell, which is 2 pi times the radius. The location of the slice is y. So the radius is going to be y, right? And then times the height of the cylindrical shell, which is y plus 4 minus y squared plus 2. The same reason as the previous one. So a quick setup. Now for part C, let me first erase those. Let me erase those now. Part C is saying that this region is rotated about y-axis. We still need to slice horizontally. Now let's see if we slice horizontally. When this slice is rotated about y-axis, we can see a washer is created. Okay, so this is the washer. Therefore, washer method should be employed. So for part C, this slice goes, it's dy again. So this slice, the limits will be from 0 to 2. And then we have the pi of the outer radius of the washer square, right? So outer square minus the inner radius square, which gives us we are going to integrate from 0 to 2. Pi of the outer is the y plus 4 square minus the inner, which is the parabola, y squared plus 2 square dy. Okay, so I hope that with the exercise here, you realize that graph is very important. Every time you have a problem, give a try to create the graph. The graph will help you identify whether shell or cylindrical method should be used. If you have more questions, please ask.